continuing on now. One thing I failed to point out earlier in this session today is the Chapter 8 objectives in the textbook are on 554. That's the application of trig functions, which I talked about earlier, right triangle, trig, law, sines and cosines, and those general topics. So then Chapter 9, which we just covered, is the polar and vector material, and the course objective or the chapter objectives for that chapter are found on page 632. And the material we're now going to talk about briefly is analytic geometry. The elements of that we're going to speak to are parabolas, ellipses, and hyperbolas in brief summary form, and a little bit about plane curves and parametric equations. The objectives for that chapter, number 10 with our book, are found on page 701. So there's nice summaries in those objective lists which might be useful to you. So let's go back here briefly to section 10.2. This is the section on parabolas. And if you want to review this, this is found in our text on page 630. And you also can review recording number 23. In summary, very, very quickly, if we derive which we did on the previous recording, if you derive the equation for a parabola based on knowing its fixed point and some fixed line, the parabola are points that are equidistant from the fixed point and that fixed line. And so that point happens to be called a focus point, very important. And this fixed line, which would be located in this illustration down at y equals negative p, is called a directrix. The equation for that has your traditional y equals x squared type of structure. But we can locate that focus if we go through the derivation, and we will discover the equation will end up turning out to be something like this: 4py equals x squared. And you can see that this is of the form y equals x squared. If this was going to open downward instead, all we'd have to do is place the focus point below and the directrix point horizontally up above. And that type of an equation would have a negative assigned here, or just the p-value would become a negative value. If you would rely on this equation, then if p is negative, this is going to be a downward opening parabola. It'll be looking like that. If p is greater than 0, it'll look like the picture I have up here. If we shift this, then the equation is going to take on the structure of a vertical shift by some distance k and some horizontal shift by some amount h. So it could look like that if it's in a shifted form. If we form the inverse of these, in other words, take this thing and roll it over the y equals x line, we could get a rightward opening parabola. Or if we turned it around, it could become a leftward opening parabola. And those equations then would be, actually the most general one of it would be the linear term is now on x, and the quadratic term is on y. And so this would be a right or left opening one. Again, if p is greater than 0, this is going to open to the right. If that p-value is less than 0, it will open to the left, shifted to a vertex location at some hk. And similarly up here. Let's see. How about illustrating this with an example? Here's a problem from the book, number 48 on 647, x squared plus 6x minus 4y plus 1 equals 0. More detail is available on this type of thing back in recording 23. So what we have to do is we have to put this in the structural form that I just showed you. So what we need to do is, here's our quadratic terms terms involving the variable x, what we need to do is complete the square on those. So what I'm going to do is I'm going to move the 4y, the linear y term, and the constant over to the other side. So that becomes a positive 4y minus 1. And I'm going to leave the x squareds effectively here. I'm just putting the linear material on the left and the quadratic material on the right. Okay, now we need to complete the square. So what we have to do with this is I'm going to leave a little space, x squared plus 6x, and remember completing the squares, a very important process in algebra, is we take half the linear coefficient, which is 3, positive 3. I suggest you write it down and circle it. Square it, becomes plus 9. And then that now, we just added 9 to the right side of the equation. So on the left side of the equation, let's keep things balanced by adding 9 over here. Now, if we tidy this up a little bit, on the right we have a binomial square. It's just x plus 3 quantity squared. And on the left, we have 4y plus 8. Now notice that this is close. Let's look back over here. This is close to this format. This format right here. You can even observe in the original equation up here that it's linear in y and quadratic in x. That's going to be a parabola that's of the traditional form, either up or downward opening. You aren't going to be able to tell for sure until after you've got the process done. Now, you go ahead and go through the process. You come down to here. We're not quite in the form of the standard equation over here. We need to factor out the coefficient on y. So we pull the 4 out in front, and then we have a y plus 2 in there equals the x plus 3 quantity squared. So here's the form. And if you lay the standard form of the equation right there with it, you can see where the vertex is and what the value, the distance from the vertex to get to the focus are. So look right here, 4 must equal 4p, so p must equal 1. That's important. The vertex, you can observe, has an h value located at -3 and a k value located at -2. So right up here, let me erase this, and let's tuck in the sketch of this. So what we're going to do is go to the vertex location, -3, -2, right over here. There's our vertex at -3, -2. Always label it. And then p is positive 1. This fits the structure y equals x squared, which is familiar territory. Opening upward. P is a positive 1. That means the focus point is 1 above that vertex. It sits right here. So the focus point happens to be at -3, comma, up 1 from -2 is -1. Then the parabola is going to roll symmetrically upward. Now notice I have not drawn any more of it yet, because it'd be nice to get a little more accuracy on our sketch. I don't know where it hits the y-axis or what x-intercepts it has. So we could do that problem either from the final form down here, find those x-intercepts and the y-intercept, or we could find them from the original form. From the original form, if I was looking for the y-intercept, how do we find y-intercepts? Point where the function might hit this line, x equals 0. You just put x equals 0 in here, it disappears this, and you're going to get, let's just do it up over here because it doesn't take much room, -4y plus 1 equals 0. Solve that thing and you got y equals 1/4 if x is 0. So we plot the point 0, 1/4. Now what's nice about knowing that point is I now know that there's a 0 to the left of that y-intercept. Has to be. And how do you find x-intercepts or zeros? You let y equal to 0. So what we would have if we let y equal to 0, over here we let x equal 0. Now we're going to let y equal to 0. And so we're going to have x squared plus 6x plus 1 equals 0. That thing either takes completing the square to solve it or using the quadratic formula. Well, let's look down here. We already took the time to complete the square. Why not come down here and let y equal 0? If you let y equal 0, most of your work is already done because you already completed the square. So if you let y equal to 0, we have 8 on the left, and over on the right we have the perfect square, and this is back in the intermediate algebra level. This is called the square root property. So if we square root both sides, we get plus or minus square root of 8 equals x plus 3, and so x equals negative 3 plus or minus 2 square root of 2. So notice the symmetry there. Negative 3, and to the right, square root of 8, which is almost 3, to the right of that spot, and then negative 3 minus square root of 8, almost 3 to the left. So I can eyeball that pretty accurately, and now I can finish my sketch, and it feels much nicer. So there it is, including the focus, including the curve, the zeros, the y-intercept, and we even could put the directrix down here, one below the vertex. So y equals negative 3 would be where the directrix sits. Okay, that's parabolas. Let's take a brief look at ellipses. 10.3. And this would be recording number 24. And here's a problem. We'll keep it simple. Number 44 on 658. You can find much more detail on recording 24. Here's a simple problem. X plus 4 quantity squared over 9 plus y plus 3, y plus 2 quantity squared over 4 equals 1. Now, without going through the whole explanation about this, what we want to do here is just go ahead and realize that this is 3 squared. This happens to be 2 squared. That's important. It's because what we have to do is we have to draw this thing. So the center of the ellipse is going to be at negative 4, a shift of 4 to the left from the origin, and a shift down of 2. So 4 to the left and down 2. So the center sits right there at negative 4, negative 2. The graph of the ellipse is going to be in a domain that is to 3 to the right and left. Notice that this 3 squared is tied in with the x term here, and 2 squared is tied in with the y term. So related to x, that's your left and right information. 3 to the left and right of this center sets up the domain for this relationship. So it'll go as far to the right as this point at negative 1 on x, and then it'll go as far to the left as negative 4, 5, 6, 7, negative 7. So negative 7, negative 2, and this point right here happens to be at negative 1, negative 2. Then from the center, we're then going to go 2 above and below that center. So we go 1, 2 above, and 2 below. And so we end up with a shape that is going to be pretty close to circular. Let me not make my scaling quite so much there. And so this would be at negative 4, negative 4. And so there's a rectangle in which is inscribed the ellipse. This ellipse has a long axis. The long axis through there is called the major axis, and the shorter of the two axes is a minor axis. One other piece of information that's very important is there are focus points that lie on the long axis. They lie on the long axis, symmetrically to the center and to the left and right vertices. The way you find that location is oftentimes that distance is called something called C, and the key on an ellipse is the long axis, the semi-major axis length, which happens to be this, happens to be in this problem 3. That 3, you hook it on to the minor axis vertex up here, and that distance 3, that length 3, falls and hits the major axis at the location of the focus. So in other words, you end up taking this distance 3, the semi-major axis length, and you lay it on there as a diagonal, and you already know this value is 2, and so what we have in this case is a 2 and a 3 like that, and we need to compute this distance to locate the two foci. So that length happens to be square root of 9 minus 4 is square root of 5. So it's a little more than 2 to the right and left of the center is where those focus points are located. The monitors went off for some reason. Okay, I'll keep talking. Now, that illustrates the fundamentals of an ellipse. Let's go ahead and just make a simple change to this equation that will dramatically change the shape, leaving that same rectangle, and we're going to end up with the other conic section, which is in section 10.4 of our book called a hyperbola. So I'm going to use that same problem with a minor alteration for a brief summary of what's involved with hyperbolas, illustrating using this example. If I still have x minus 4 squared over 3 squared minus y plus 2 squared over 2 squared equals 1, we've dramatically changed the shape. Same rectangle, happens to be centered at -4, -2, 3 to the right and left of that, and 2 above and below. We draw the rectangle. That's called the fundamental rectangle. And now, for the hyperbola, we lay diagonals in here. Oh, one other comment before I forget. In 10.4, this is found in our book on page 659, and this is recording number 24 for more detail about the development of this, including completing the square to get this standard form of the equation. So, here we go. We now lay diagonals in here through that rectangle, through the fundamental rectangle, and these are called asymptotes. These are called asymptotes. Now you can look here and see it real easily that there's a distance 2 there, a distance 3 here, and you can see the slope of this upward trending diagonal to the right, a slope of 2/3 with some y-intercept. So oftentimes you need the equation of those asymptotes. And so right away what I usually do off on the side is I usually know my center is at -4, -2, and so I use the point slope equation of a line. So y minus a -2 becomes y plus 2 equals the slope 2/3 times x plus 4. So there's the point slope equation, and then you can solve that for its slope intercept form. So you have y plus 2 equals 2/3 x plus 8/3, and you move 4 over to the other side, 2 over to the other side, which is 6/3 negative. And so I believe, if I did my arithmetic right just then, and no guarantees if it's correct or not because I don't have students here to check me, minus 6/3 is 2/3, I believe. It looks okay based on what I'm seeing on the sketch here. It looks like a y-intercept of about 2/3. We also need the equation of the other asymptote. I can leave that up to you. It's going to have a slope, though, of negative 2/3. So just leaving it at the point slope form, y plus 2 equals negative 2/3 times x plus 4. Clean it up, have the equation of that asymptote. Okay, now, if the x information here is positive with this equation and the y information is assigned negative, then this is going to be a right-left opening hyperbola. And it has vertices. These happen to be the vertices right here and over here. It's a right-left one. The graph looks like this. They approach those asymptotes. This is one wing of the hyperbola here to the left, and there's another one sweeping out to the right, like this. That's a picture of it. And the long axis, the axis through those vertices, is called the transverse axis. Transverse axis happens to be y equals negative 2. The focus points lie on that axis, symmetrically inside the curve, inside the wings, like this. And the easy way to find that focus length is you do the following. The distance from the center to the focus point, the center to the focus point, let's call it C again. It's real easy to find with a hyperbola. What it is it's obviously longer than the 3 or the 2 on your rectangle. And the way you find that is all you have to do is look at the sum of what you see here in the denominator. The square root of 3 squared plus 2 squared is the square root of 9 and 4 is 13. So that's the distance to find the focus points. This left focus point over here is going to be located, notice, this is labeled negative 4 right here. I had that wrong on the picture. It's negative 4 minus square root of 13, comma, negative 2. And the other one is going to be at negative 4 plus square root of 13. Anything else I should say about that? We have the focus points located, we have the asymptotes defined, we have the fundamental rectangle, which is absolutely critical, and you see that it's a left-right opening one because of the x terms being treated positively and the y terms negatively. If this was reversed, if this term was positive in front, subtracting this x term, it would be the same rectangle and the graph would be an up-down opening one, like this. And the equation of that one would be your y plus 2 quantity squared over 2 squared minus x plus 4 quantity squared over 3 squared equals 1. That would be the up-down opening one with the positive term being on y. Okay, I have one other topic. How much time do I have approximately? About 10 minutes. Okay, let me just very quickly touch on the very last section, which is the plane curves and parametric equations. Plane curves and parametric equations. This is going to be very abbreviated. Section 10.7 out of our book, page 687. Plane curves, that means two-dimensional curves, don't have to be functions at all, and parametric equations. Recordings number 21 and 22 cover this in quite a bit of detail. Here's a simple problem out of the book, and like I said, I'm just giving you a very quick comment on this. If x is equal to cosecant of a parameter t and y happens to be cotangent of parameter t, what we want to do is generate the plane curve out of this. Now you can't do this with your calculator because we don't have a, well, you can't do it in the form that you see right here because we don't have a cosecant function built into our calculator, and we don't have a cotangent function built into the calculator. So what we need to do is to treat x as behaving like 1 over the sine of the parameter t. And the reciprocal of cotangent is tangent, so we need to use 1 over the tangent of t if we're going to use our technology on that. Now the window settings I'm going to go ahead and use on this. I think I will go ahead and just throw this into the calculator in the interest of time. So what I'm going to do is I'm going to be in radian mode, and I'm going to, first of all, I'm going to go to my mode screen, and I'm going to change this to radian mode, and then I'm going to come down here onto parametric mode, and I'm going to go to y equals now, and I'm going to clear these out. And so here I can now define x and y separately in terms of a variable t. And I'm going to go ahead and put in 1 divided by sine of t. And for my y values, I'm going to put in the reciprocal of tangent, or excuse me, reciprocal of cotangent, which is tangent. 1 divided by the tangent of t. And now, in radian measure, I'm going to set a region from negative pi on t to pi, and I'll let tick marks be every 0.05 radians, and my viewing window negative 3, 3, 1, and negative 2, 2, 1. I think you're going to be excited when you see this curve. Watch, here it comes. Looks like a what? It's looking like a left-right opening hyperbola. Looks like a left-right opening hyperbola. And there it is. And the reason it shows these diagonals is because it's actually in connected mode. So it's trying to plot a point way off on the end over here to another point that then transforms way up to here, and it ends up shooting a straight line across there. If you don't want those to show, all you do is come over to the far left here and hit enter with your calculator. And I have to cycle through these different choices with enter. There, now I'm in dot mode. Now if I hit graph, you won't see those asymptotic, those diagonals that appear to be asymptotes, even though they're really not quite the asymptotes. Okay. So what we ended up with, kind of interestingly, is this ties back to the hyperbolas that we just spoke of as far as its actual graphical interpretation. And you saw that this equation was, or the graph of this thing, this plane curve that you see, is definitely not a function. Doesn't pass a vertical line test. So this is called a plane curve, and you can generate those very nicely from parametric modeling. There are other topics in this chapter that are really important that in the course we did not have time to talk about. What goes on is what would happen if we took one of these shapes like this and we rotated it. So it's not nice left, right, up or down type of a thing. Same thing with the ellipses or the other shapes. And so typically in these textbooks you will find a section on rotation of axes. So that's in section 10.5. And then also all the conic sections that we talked about earlier, the parabolas, ellipses, hyperbolas, also can be more simply drawn and more simply developed in polar form than in the XY form in which we studied them. So there's a section on that in the book, but unfortunately we didn't have time in this course to cover that. So that pretty well wraps up a very quick summary. This is the third session of the review sessions for this course. So good luck in your future math courses.